So what we're actually going to be talking about today is graph neural networks. So this is another approach for kind of the vertex classification, prediction, label prediction, everything else that we kind of talked about before. So for this, fortunately, I'm not going to be attempting an implementation because yeah, the last one was pretty painful and the results were less than exemplary. And there's good discussion in the forum about it. But it's interesting stuff though, which is why I kind of want to cover it. It's a different, somewhat a related approach, and kind of, if anyone's taken more machine learning, data sciencey kind of classes, you probably have some experience with neural networks in general. So this is kind of a different way that we might think about, neural networks and, in terms of classification, prediction, everything else. Specifically, instead of like kind of that structured kind of net, kind of the structure of the actual like neural network that we would commonly see in like your typical feed forward network or like convolutional network or whatever else. That kind of regular structure is, with graph neural networks, we kind of toss that to the side and do this, assume that the graph itself is that neural structure. And so what I mean is, we'll get to that in a bit. So let's consider your basic. So for people who aren't, we're going to do a little background into neural networks, in general, just for people who are not super familiar. So let's talk about neural networks. I mean, the basic idea behind neural networks is we have a neuron with some output, which is a function of several inputs. So let's, inputs. And so generally, the output, let's just call it the output, is some nonlinear function of these inputs and essentially some weights on these inputs. I think it's, let's call it W times I, more or less. So we'll use a little different notation go forward. So, I mean, the basic idea is we have a neuron which is a function of some number of inputs, each weighted by a certain amount. And you get, you give some nonlinear activation function kind of based off that. So like a sigmoid-like function, something like that. Or, we could have, if we're considering hyperbolic tangent or something, it could be something along those lines. But yeah, so the basic idea is we have some output that is a function of inputs, nonlinear function specifically. And so the network aspect comes into effect is that we have multiple neurons connected together. So we might have, say, some inputs. So this is kind of basic idea. We have some number of inputs. So let's just say we have some x naught, x1, and these inputs are attached to some number of neurons in some number of layers. So again, kind of keeping it relatively basic. So we might attach our inputs to this, and we might have like the actual inputs. So this might be our input layer, and then we have the actual inputs going into those input neurons. And we're assuming full connectivity here, kind of the structured notion. And each of these will be connected to some number, and then we'll have some number of layers. So these are commonly called our hidden layers. And then we have essentially our output layers, or output layer. So again, basic kind of structure. So let's call this O naught and 0 or O1, and these would be, again, function of this. And so generally, yeah, so we have some inputs. The inputs are fed into this input layer, which has some nonlinear activation function, which outputs, so it outputs the same value, but with different weights for each separate neuron. So this would be, let's call this like W00, H2, and this would be like hidden neuron H1, H2, or H naught, H1, H2. So that would be a hidden layer. We'd have some number of hidden layers, etc. And usually we'll see like some kind of bias, which again, we have our bias and some number of weights associated with that bias. And so that's kind of the basic structure of your typical neural network. I'm sure a lot of people in this class have more familiarity and better background with neural networks than I do. I hadn't worked with them I did a project with the Navy where we were controlling some underwater, essentially unmanned submarines using neural networks as input controls. And that was about like, I don't know, 12 years ago, 10, 12 years ago or something. Was it? Yeah, something like that. So that was a while ago. That was the last time I ever used neural networks. And based off, I was looking up stuff for this class, this lecture, there's a lot, or, a lot happened within 10 years. I'll give them that. Definitely a lot went down. Graph neural networks being one of them. But yeah, so like I'm talking about, neural networks and the whole general kind of concept. Yeah, so the basic, so essentially we have like an output that is a function of inputs plus all these, hidden layers. So we have these outputs, which are essentially, so an output is a function of essentially, all the weights times all the intermediate steps. So, commonly written like weight times h, or function of weight. Yeah, let's just keep it simple. Function of weights times h, where h is essentially the output for each of these neurons. So maybe you'd write this as h naught. This input is actually x1, x naught, and this would be like, our h naught hidden layer, but really our input layer. But yeah, for consistency, that's what I'm saying that. Yeah, plus bias. I think it better probably. So like, so if we consider like a layer k, so the output of a specific layer k is a function, so we'll consider sigma to be a nonlinear function of the sum over the weights for each of these times the prior layer plus the bias in that prior layer. And that's probably a better way to denote this, where our like x is like h naught for k equals 0, and our output is h for k. So if we have k layers, that's essentially what we have. So this is referring to specifically the input layer, our output layer, and our intermediate layers, where we essentially solve this intermediate layer as a function. So the output for a given given neuron in this one of these hidden layers is a function, a nonlinear function of the sum of the weights times the outputs from the prior layer plus this bias. That gives us overall, a generalizable kind of neural network that we can do all kind of fancy stuff. We can do modifications and specifically by how we set up our activation function, how we set up, our input layer, how we structure everything. Can do a lot of interesting stuff for various, a million different applications, as we found out over the last 10 years. Yeah. So that's just the basic structure of your, normal neural network and the way we actually train this. Essentially, we determine some loss, some error, determine some sigma, and that will be just essentially a function. So like the sum over all outputs. So I within, let's just say, the output layer of the outputs I minus some training value I. maybe like have a square or something like that, but yeah, whatever. Uh, well, I mean, in this instance, you wouldn't. The reason why, well, I mean, yeah. But essentially, so you have some error or some loss, as it's commonly called, and use this for gradient, essentially just gradient descent. And essentially, specifically update our weights and biases. So this is called essentially backpropagation. So like your typical prototypical neural network uses some kind of variation on this for training, where essentially we just look at, our activations, and based off whatever our activation function is, do some form of gradient descent to modify our weights and our biases. Oops. And from that, eventually we will, so for this function here, we also consider, and the way the training is specifically done is kind of variations in how it's done, but generally speaking, if we consider just a single data point, we perform backpropagation relative to that specific data point. We do that over all possible data, all possible training data, and then that's essentially, will eventually converge on average, the average error. Let's call this loss in this specific context, where the error itself would probably be more accurately stated as kind of the sum over all losses over all training data T, more or less. All right, so let's extrapolate this general idea to graphs. So graph neural networks. So let's consider some graph structure here, some arbitrary graph structure. We have this V here, and then we'll kind of create the neighborhood around V, and W, Y, Z. Then we'll have an S and a T. So we're going to be considering kind of from the perspective of this V right there. I probably shouldn't do dotted lines. They're difficult to erase. Okay. All right. So the basic idea here, kind of considering our prior kind of neural network, is that we're essentially having this graph itself be that specific structure of the neural network. So graph neural networks kind of very, very broad. So there's dozens and dozens of different kind of formulations for the same basic idea. So we'll try and keep it relatively general. So last class we kind of saw from the perspective of our vertex V here. So from last class, we were doing our kind of label prediction and classification, whatever else. From last class, we predicted essentially some output on V, which was dependent on the neighborhood of V, along with, so when I say dependent on the neighborhood of V, we're talking about, the features of its neighbors, along with, say, some feature set of V itself. So that's essentially what we're doing. We're doing some kind of prediction. We had, some predictor, some feature set. So predictor, some feature set for our specific vertex V, where the feature set, we consider from the perspective of V, or just the global set of features. But essentially the idea is we fed these into some classifier, some predictor, whatever else. And it could be a trivial one or something complex. It could be a neural network itself, realistically speaking. And then we got some prediction for V, and whether we're in the context of supervised, semi-supervised, unsupervised, it's relatively same approach, more or less. It's kind of how we, we're working with this problem now. So, I mean, the idea, so for this class, the graph neural network basic idea, and I don't know how to put this as simple as possible, but it's something along the lines of more so we propagate outputs slash states along edges with, so when I say we propagate output states, that's per vertex states with vertices acting more or less as neurons, or more specifically just neural networks. So that's generally the basic idea behind graph neural network. So one way to kind of structure this, so if we consider our graph here, and for considering, say, the graph neural network kind of representation, when we consider from V's perspective, we can kind of reformulate this graph as, from V's perspective, as a neural network that is essentially outputting something specific for our vertex V. So if we look at our vertex V here, essentially we can say that there is, some either neural network, a full neural. So again, like I said, there's multiple different kinds of formulations. So we could have a deep neural network per vertex, or have just like a simple neuron activation or something like that for each vertex. So we'll just denote this as sigma, so some nonlinear function. So it could be a neural network, could just be simple neuron, or just nonlinear activation function essentially. So from V's perspective, let's redraw this. So we have, so from V, we have that neural network or whatever else. We have some output vector essentially. So in context of this being a neural network, this would be essentially our output layer. And so kind of, we're assuming that we're propagating, we're representing the neural network structure along the edges in our graph here. So from V's perspective, it has neighbors U, Y, and W. Let's kind of go down here, give a little more room. So U, Y, and W. And again, we have kind of the same notion where we have some, there we go. Okay, there we go. So again, the same idea. We have some kind of, neural network associated with each vertex. So this is essentially one of the hidden layers for our vertex V. So we'll talk about kind of how this is more explicitly formulated in a second, just kind of to draw the more representative notion here. So U doesn't have any neighbors except for V, and normally what we would consider is some layer, some number of layers, which we'll just call K. So we'll have K total layers, including input output layers. And in each layer, we essentially have some input that gets propagated to the next layer, more or less, along the edges specifically of the graph structure we're considering. So for Y, neighbors are Z and V. We'll just, for consistency, just redraw V there, so Z. And then our W, Z, T, S, and V. And T and S. So here we kind of have the representative notion of a neural network associated with vertex V. So what is this? This is our output layer up here. This might be considered, a hidden layer more or less right there. And let's call this our input layer. So there we go. We have a 3-layer neural network associated with vertex V. So we get some output based off of essentially some K-hop neighborhood more or less. So we're explicitly showing all the dependencies that we have here in terms of each vertex is, if we're considering it in the context of, the neural network associated with the vertex, each of the vertices within that network are, a function, their output is a function of their neighbors, which is a function of, their neighbors and et cetera, all the way up to whatever our k is. And so that essentially this is kind of the structure more or less that we have in the general case for graph neural networks. So to kind of get like a formulation going, let's throw down some notation. So this is going to be more or less consistent. I'll try and keep it consistent with the paper I'm going to post, which is just kind of a broad overview of, the various different graph neural networks. So I'll try and keep it consistent with that. But so we have, this should be an O, not a sigma. I draw, okay. Yeah, so I drew a sigma there. I was wondering what was going on. Okay, so this is an output. So this output V. So these are all going to be from the perspective of this vertex V. So that's essentially its output. So it could be, one single output, or like we saw before with the above neural network, we could have, O0, O1, etc. So some arbitrary number of outputs. So that's why we have this specifically as a vector. And then H is what we'll call hidden states. So we'll see kind of like mathematically how that comes into play in a little bit. But essentially for, say the vertices within the hidden layer there, they are going to have some kind of hidden state associated with them, essentially, their specific output for a given layer. So like, we see vertex V kind of repeated, or, we see vertex V right there. Even though, so we're considering both the output and more or less. Well, I guess if it was, we're considering a larger neighborhood, it could be, the point here is that a vertex could be in an arbitrary number of hidden states. So hidden state is going to be not just, a single value, it could be multiple values within the context of a neural network, associated with some other vertex. Then we have more so like our explicit features. So features might, come into play. Again, we'll kind of get into the mathematical notation of that specifically, but it's kind of related to the notion of, say, this input layer, where you have some set of features associated with each vertex. So kind of consider that as the features in the context of, what we saw before with the general feed-forward neural network that we looked at up there. So we have our hidden states, which is essentially just outputs within the hidden layers of this graph neural network. We have our features. And we could also correspondingly consider edge features as well. So if we have some edge like E equals UV, that would be our edge features, but just sticking with the notation in that paper, a X co V, which is essentially just, again, edge features. So we aren't going to get into a neural network using edge features, but within the context, so again, broad class of different graph neural networks, and some of them can use with how they essentially combine neighborhood features or neighborhood outputs, hidden states, everything like that, could combine edge features along each specific edge. So we could have like a feature associated with this edge here, and that would, modify the input from our output, our hidden state of W here into whatever the function is associated with V in that output layer, would modify that value, kind of associated with that. And so we also have, if we're considering from the perspective of a vertex V, we would also consider, say, hidden states of its neighbors. So this is just kind of notation wise. So we'll kind of gloss over this again in a little bit. So hidden, let's just say neighbor states. neighbor states, and then x any of the equals neighbor features. So that's, I mean, that's the explicit kind of, notational variables that we're going to be considering. And generally speaking, the state of a vertex is going to be a function of possibly its features, possibly the features of its neighbors, state of its neighbors, and or the edge features, then the hidden state of its neighbors, then the features of its neighbors. So the state of a vertex is a function. So essentially we're just saying that the state of a vertex in terms of its output, as we kind of notice up here, is potentially a function of, depending on the explicit formulation of the actual, graph neural network. So take a look at the paper. You'll see a dozen different formulations in terms of how everything's kind of aggregated together and information. So the differentiation is basically how information is aggregated through the graph from, the neighbors of a vertex to a vertex. So we're just going to look at a relatively simple one where we just take a simple average and not care about edge features and stuff like that. But just we're looking at here specifically in the general case. A vertex, state of a vertex is a function of features and the state and features of its neighbors. And then we could also consider the output of, the end of the day output. So as we have it drawn here, the output of this vertex V is essentially just, kind of equivalent to, the calculation for its state, just as we have. When we discuss, and when we work through it in the future, that's generally how it's going to be for our specific example. But that's not, in general, the case. So there's other explicit kind of formulations that include, say, some separate function, which we'll define as G, where the output for a specific vertex is going to be a function of that state and the features of that vertex. So for us, for our future example that I promise we're going to get to in a second, essentially, the output is just going to be equal to the state more or less. So keeping it relatively simple. And so terminology-wise, F is generally called, transition function. So how states change and how information flows from vertex to vertex along the edges of the graph. So this is essentially just updating states. And then our G we'll term as the output function. And obviously we aren't updating states, we're updating outputs. Again, kind of from, dependent on the state of the vertex and possibly the features of the vertex. So generally speaking, if we consider, let's call this the general approach. So this is kind of corresponds to basically the notion of, the kind of similar to what we saw before, but kind of more in the general kind of graph neural network. We'd have some K neighborhood essentially. So it's kind of like an iterative approach more or less, but we're kind of updating things a little differently, a little more explicitly here. So consider like global H, well, not O, but H, X matrices. So these essentially are matrices containing all features for all vertices, or possibly tensors, all features for all vertices, and all states for all vertices. So essentially what we're doing is we're iteratively updating. So features we're considering to be static. So these are inherent features to each vertex, like, consider social network, demographic information, that kind of thing. Where our states are the actual important parts of the neural network in terms of, information flowing through the network. So our goal is iteratively updating this K, where, we can consider H. So pretty much what we saw before, in terms of updating something associated with a vertex and that iterative formulation for classification that we saw last couple classes. So our H is going to be just essentially, more or less, we consider, say, a global transition function instead of just this local transition function, H of t and x. So essentially we update our states based off of a function of h of t and x. And so where's the actual kind of learning coming into play? Because we can just, this kind of the unsupervised aspect, which we kind of saw before, where we're just, we might, with like, say, label propagation, where we're in an unsupervised setting, we're just updating as a function of, the prior state, more or less. In this instance, if we're considering like a supervised approach, as generally speaking is done with neural networks, we can consider some kind of loss function, which will essentially be, if we consider a sum over all possible, essentially all possible outputs, more or less. Let's say all outputs, or the loss for a specific vertex, I guess, from the perspective of a specific vertex. Let's say the cardinality of that, that output set. OI, where obviously for a specific vertex, so the loss of V, so where Ti is, again, we're considering the supervised setting. So this is some kind of data associated, so some explicit, data that we have that we expect to be output based off of, this being a training set kind of situation, I guess you could say. So this would be like the ith data in training set, I guess. I don't know. Training set for vertex V. And then O of I would be the ith output from the graph neural network on that specific vertex V. And then from here, depending on what our activation functions and everything else are, to actually update. So the approach is, well, again, we're updating, we're going to be, to actually update, essentially, like we kind of saw up here, the driving kind of updates that are occurring are going to be in these weights that kind of control, the level or the, how information is essentially flowing to a certain degree through the neural network itself. So to actually update, we update essentially some weight matrix W. So this weight matrix W holds all the weights that kind of control how information is actually flowing. So on each of these, we'll have, some weight associated with it. And so this would be like that hidden state of vertex W times the weight input to the, the neural network, or just the neuron associated with vertex V. And essentially that's, more so the same thing we saw before. Again, basically here, we're summing up for each of these neurons, we're summing up the inputs in terms of weights times, the output of the neuron in the prior layer. summing up, putting it through some nonlinear activation function, and outputting whatever. So let's take a look at kind of a basic, formulation here. So like I mentioned, formulations are kind of dependent on aggregation and everything else. So how we aggregate messages past the hidden states and outputs and everything else through the network, aggregate by essentially just averaging, and let's just say messages. So like a lot of the stuff you'll read in terms of graph neural networks is essentially, terming it as message passing, meaning that, message from W, output of whatever, its neural network, is kind of the message being passed to that next layer within the broader neural network. So here's our basic formulation. We're going to aggregate by averaging messages. So, like kind of mentioned before, if we go back to the, this we have up here, let's kind of do it from the perspective of this representation. So let's bring it on back down. Let's see if we can do this without breaking. Copy. And, oh, things happening. Okay, here we go. Let's see. Paste. Oh, look at that. All right. So, I mean, we're doing all right here. Let's try and move this a little bit. Okay. All right, let's shrink it down to getting all right at this. Okay. So here we're going to be considering from the perspective of this. So essentially, recall we have like kind of the equivalent notion of input layer, hidden layers, output, more or less. I mean, there's some nuances there, and it's highly variable. But to keep everything simple, let's consider, essentially outputs, activations, everything else. So from the perspective of this vertex V. So essentially, if we consider the hidden states, so when we're talking about hidden states associated with some vertex, more so, we're going to be considering just updating these hidden states from the perspective of that specific vertex. So on a per layer basis. So the hidden states of layer 0 is essentially just going to be, the features of all the vertices, let's just call it x0. That's notationally it's a little whack, but yeah, it's good enough for our purposes. Essentially, these are, so that'd be xv, xc, dot, 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 dot. So essentially the inputs are more or less just the features for that, layer there, that, the layer not is more or less. Okay. Say more or less a lot, I know I do. Okay. Here we go. And then hidden states associated with each specific layer. So hidden states, associated with this layer, and well, I mean, really, that. I guess we consider these hidden states. So the states associated with that is going to be kind of like what we saw before. So we have some nonlinear activation function, and we're going to be updating the weight matrix for k times. So again, we're aggregating just by averaging messages. So the sum over h, essentially the hidden state associated with some vertex u for all u within the neighborhood of the vertex we're currently considering, over the size of that neighborhood. So I can't really read this too well. Let's see if I can. U within the neighborhood, over the size of that neighborhood. And so this would be kind of the basic notion, basic representation. I guess to keep it equivalent to what we had before, let's also throw in a bias term. So same idea, bk h and k minus 1. So let's move that over so we aren't on the edge there. So plus BK HK minus 1. And essentially there we go. And let's say some bias matrix B. So this here is more or less just the equivalent to going all the way back up again what we had right there in terms of the outputs of each neuron at each hidden layer. Again, some nonlinear activation function, which is a function of some weight matrix, some number of outputs. So something I didn't make explicit when we were considering the outputs from a specific layer here, as we can say, there could be some arbitrary number of those, and essentially that's what's being controlled by this weight matrix when we're doing this multiplication of this, vector times that weight matrix. And then obviously the output is just going to be h of k. So kth layer is our output. So this is kind of the basic representation. And so from here, we basically have these two as to what actually gets trained. So similar fashion to what we saw, depending on the activation function, to figure out the gradient, do gradient descent. So there's a couple things to note. W is consistent, W and B really. B are consistent across the network. So what I mean by that is we have a WB associated with this specific vertex V from the perspective of what we have drawn right here. But if we're considering our total graph, we could be, say, predicting or classifying vertex V or vertex Y or vertex W, any one of those. And this notion is that the weight matrix and this B are what's consistent across the network. And that's essentially going back to our loss function here. And we said specifically, if we're considering the loss over all possible outputs, over all possible vertices in terms of what's getting output, we're kind of doing gradient descent on a per vertex basis, but across all possible training pieces of data and across all possible vertices within our network. So in general, like I said, W and B are consistent across the network. And so the interesting aspect to point out there is that essentially the variables associated with the global graph neural network can be in fact sublinear in the size of the graph or the order of the graph. So that's something could be interesting. That's why graph neural networks kind of came into attention, because you could have some powerful kind of learning mechanism that the amount of effort you put in is less than the representation of the graph itself in terms of complexity of the variables and everything else. Okay, so WB are consistent across the graph. Aggregation can be done in any number of ways. Any number of ways. So, I mean, the basic idea being, for all these, whatever's going on in there can be swapped in and out and everything else. We could also say add, our features associated with the edges of, where the messages are being passed, essentially, in addition to having some, weights defining pretty much everything that's going on in terms of, passing messages to update states across the different layers of the graph neural network. So aggregation and activation function, everything else can be done in any number of different ways. learning for WB is similar to backpropagation on non-graph neural networks. So let's just say that. And there's also approaches for like unsupervised, semi-supervised learning where we aren't so much in saying we're going to have explicit features, but we're trying to say define, in terms of the output function, defining some kind of similarity metric between vertices, kind of dependent on how we parse the output. So we want to say that two vertices who are similar in a certain way, like say number of neighbors or location in the graph or some centrality metric, should have similar outputs from their specific computational network, neural network. So that's kind of an unsupervised approach, more or less, but kind of it's highly dependent on the how you define everything else, and we aren't going to get into the nitty-gritty details. And there's more than enough information online for you guys to look. So we're just going to kind of keep it relatively broad here. So WMB consists across the network. Aggregation can be done in any number of different ways. Activation function as well, how we parse features, everything else. One thing I'm not sure I explicitly noted is that when we have our features here, as is the case with pretty much all neural networks, the inputs have to be, as opposed to like say a random forest, inputs have to be some, usually a floating point value of some kind. Otherwise, we can't do like, calculation for whatever our activation function is. So, how to like actually extract and represent features is, consistent with other neural networks is one of the big challenges with graph neural networks specifically as well, depending on the context and everything else, how it's being used and whatnot. But generally speaking, input features have to be some, floating point numeric value. Otherwise, they can't be necessarily parsed. I mean, maybe there is, I don't know off the top of my head, maybe there is some kind of representation or some function that like lets us do a bunch of weird stuff depending on the inputs, and it's non-numerical based, but I don't know. I've never seen, I don't want to say generally speaking, because there's like a billion different kinds of neural networks. So, but I don't think I've ever seen it personally. But I don't want to say that's always the case. But yeah, so generally speaking, features have to be, some floating point value, as with, neural networks in the general case. Yeah, and like really, so the takeaway here is, based off of everything else, overall similar power to other more structured neural networks, but we include the additional kind of edge, let's say per vertex edge based or like neighbor based computation graph. And that's kind of the big differentiation is the for each vertex that we're trying to get some output from, their perspective in terms of their neural network or their outputs is a function of more or less their, n k-hop neighborhood. So we include the addition null per vertex edge-based computation graph. Again, that's dependent on the actual graph itself. So that's all I want to talk about today. So I'll put up the papers I mentioned, and probably not going to do like hands-on coding. I might try and find something that would be useful for you guys if you want to kind of get into it. Maybe like a tutorial or something. I'll probably put that up. But yeah, so that's it for today. Hopefully this was, interesting enough.